Okay, hello everyone. In today's reading group, we are going to discuss the topic graph neural networks and the non-Euclidean machine learning. So our discussion consists of the following three parts. First is a gentle start, in which we will give a brief introduction of the non-Euclidean geometry. And then I'm going to introduce a paper in NeurIPS 2019 called Hyperbolic Graph Convolutional Neural Networks. And then I'm going to introduce an ISML 2020 paper called Constant Curvature Graph Convolutional Networks. Okay, now let's get started and move to the introduction part. So in this part, basically we are going to discuss four key questions. What is the Euclidean geometry and what is non-Euclidean geometry? And what are some of the examples of the non-Euclidean geometry? And finally, we're going to introduce the product space. So for the examples, essentially we are going to introduce two commonly used non-Euclidean spaces, which are elliptic geometry and the hyperbolic geometry. And now let's come to the first question. What is Euclidean geometry? So a formal definition of Euclidean geometry can be Euclidean geometry is a mathematical system based primarily on a book called The Elements, written by a mathematician named Euclid. And if we want to give an informal definition, then we can say that Euclidean geometry deals with point lines and planes and how they interact to make more complex figures. So for line, we usually represent it with this R1. And if it's a plane, then it's a two-dimensional stuff, which is R2. And for space, then usually we're talking about a space with dimension more than 3. Now let's see, for the Euclidean geometry, it will be very important to know what are the key postulates of the Euclidean geometry. So a postulate means a statement that is assumed to be true. So for Euclidean geometry, there are four very basic postulates and one very important postulate. So I'm going to introduce them one by one. As we mentioned before, Euclidean geometry deals with points, lines, and planes and how they interact to make more complex figures. So here we first introduce how this Euclidean postulates that defines how the points, lines, and planes interact with each other. So the first postulate states that through any of the points, there is exactly one line. And then the second postulate is that through any 3 points, not on the same line, then there is exactly one plane. And then the third postulate is that a line contains at least 2 points. And the last one is all the right angles are congruent, which means all the right angles are considered as exactly the same. So these 4 postulates are very obvious and very easy to understand. And now let's move to the last and also is the, we can say it's the most important Euclidean postulate, which is called the parallel postulates. Basically, it states that given a line and a point not on that line, there is exactly one line through the points that is parallel to the line. So for example, we can see that this is the line, the given line, and this is a given point, then we can only find one line through the given points that is parallel to the given black line. So this postulate is very important. And we can also say that the Euclidean geometry is geometry in which the parallel postulates hold. So for the other geometries, such as the elliptic geometry and the hyperbolic geometry we're going to discuss later, they in these two geometries, these parallel postulates does not hold. So this is the these are the basics about the Euclidean geometry, and we are already quite familiar with Euclidean geometry, and I think most of the math we learned so far is on the Euclidean geometry. And then let's consider what is a non-Euclidean geometry. So even the Euclidean geometry can almost sufficiently describe the word that most of us deal with day to day. It is still very important to study some other geometries, and these kind of non-Euclidean geometries will also have many practical applications. So basically, we can say that non-Euclidean geometry is any geometry that uses a different set of postulates than the Euclidean space. So in the Euclidean geometry, the lines, planes, and operations are also defined differently. And we should also note that here, different set of postulates does not mean that all the Euclid's postulates cannot be satisfied. So as long as the postulate sets have some difference, as long as they are not exactly the same, then it will be fine. So this different set of postulates does not have to be does not have to be an orthogonal set of postulates than the Euclidean space. Now let's take a look at some examples of the non-Euclidean geometries. So if we category by curvature, then we can have three types of geometries. One is Euclidean geometry, one is elliptic geometry, and the last one would be the hyperbolic geometry. The later two are the non-Euclidean geometries. So for the Euclidean geometry, we can imagine that the Euclidean space is a flat space where we can have three important properties. One is that the summation of all the angles of a triangle is equivalent to 180 degrees. And also we would have the Pythagoras theorem, which states that the x squared plus y squared equals z squared. So x and y are the two short edges of a triangle, and the z is the long edge of this triangle. And the last important property is that the Euclidean geometry has zero curvature because it is a flat space. And then for the elliptic space, we can, yes?
So this is only holds when it's like a triangle with 90 degree, right?
What do you mean by? Yes. So for the Pythagoras theorem, the condition is that we have a angle with 90 degrees.
Okay.
Yeah. And then for the elliptic geometry, we can regard it as a space that curves inward. So for this geometry, we would have the summation of angles of a triangle would be large than 180 degrees, and it does not have a Pythagoras theorem. So if we consider we have one angle equivalent to 90 degrees, and then we would have x squared plus y squared larger than this z squared. And for the elliptic geometry, since it curves inward, it just have the positive curvature. And finally, we have the hyperbolic geometry. So we can consider the hyperbolic space as a space that curves outward. And then the sum of angles of a triangle will be less than 180 degrees. And we also cannot have Pythagoras theorem, but this time the x squared plus y squared would be less than z squared. And also we would have negative curvature because it is curves outward. So this would be this would be the basics of Euclidean geometry, elliptic, and hyperbolic geometry. And there will be a lot of different models for the hyperbolic geometries and the elliptic geometries. And in the following, I will introduce two of the most popular elliptic geometry models, which are spherical model and stereographic model. And then I will introduce two of the most popular hyperbolic geometry models, which are Poincare disk model and the hyperboloid model. So also we should know that when we define a space or we define a model, it will be very important to clarify what is a point and what is a line and what is a plane, and some important operations such as the inner product and the distance measurements. And the last important thing to study is what are the postulates for the model we defined in non-Euclidean geometries. So first, let's take a look at this spherical model. So for a spherical model, the main difference between the spherical geometry and the Euclidean geometry is that instead of describing a plane or a flat surface, a plane in the spherical model should be a sphere. Then for a line in the spherical space, it is also defined differently than the Euclidean space. So for a line in a sphere, it should be a great circle on the sphere. So for example, we can see this great circle. So a great circle means that any circle on a sphere that has the same center as a sphere. So for example, if we have this kind of circle like this, and then we can see that the center of this circle is this point, but the center of the sphere is this point. So therefore, this cannot be regarded as a line on a spherical model. But this black circle, since it have the same center as the sphere, so this black circle can be regarded as a line in this spherical model. And for points, the points is defined in the same way as in the Euclidean space, but we have one more constraint, which states that a point should be on the sphere of this spherical model. So this is the constraint we should have. And for the spherical model, the dot product operation is defined exactly the same way as in the Euclidean space, but then for distance, it is defined differently than a distance on the Euclidean space. So the distance is defined as the arc cosine value of the inner product of 2 points. So here U and V are 2 points in this spherical space. Then let's take a look at the postulates in the Euclidean space and see if they can still be satisfied in the spherical model. So for the first 4 simple postulates, we can see that it is still true for the spherical model. So we can tell by these 4 examples. So through any points, there is exactly one line. So if we have 2 points on the surface of a sphere, and then we can only find one great circle that pass through these 2 points. And through any 3 points that are not on the same line, there's exactly one plane. This is also true. So we can see that if we have 3 points, then we can only find exactly one sphere that such that all of these 3 points are on this sphere. And a line contains at least 2 points. This is also true, and it's actually quite obvious. And all right angles are congruent. This is also true. So we can see that these 4 postulates can still be satisfied in the spherical space. However, for the last, which is
mean, and what does congruent mean?
Congruent mean they're exactly the same.
What does how is the same defined? And also, what's the definition of plane?
The definition of plane in this spherical model is a sphere. So imagine that if we consider we have a ball, and then the surface of this ball is a sphere. So that's the definition of a plane.
So in spherical model, do we assume everything lies on a single sphere, or do we also assume that there may be multiple spheres? That is the space. So is it more like a 2-dimensional space, or is it more?
So when we say a spherical model, it's like a 2-dimensional stuff. And if we consider a higher dimension, then that would be called a hyperspherical model.
So here then, the second postulate, can we also say that any number of points that are not on the same line, there is exactly one plane? Is that also true, given the definition?
So for the space generated by this spherical model, I think this should be true. But if we move to the hyperspherical model, then given any, for example, 4 or 5 or even more number of points, there might not be a plane.
How is the, let's say, 4-dimensional spherical model defined? Is it all the points that are at the same distance from the origin?
So if, for example, we have a hypersphere, let's use for example 4-dimensional stuff, and then each x is x1, x2, x3, x4, and then for the space that's generated by the hyperspherical model, all the points are the points such that x1 square plus x2 square plus x4 square, it's equivalent to some certain distance, which is the radius of the
So
hypersphere.
if it is R4, then how is the plane defined there?
Then for that one, for the spherical model, then we would have a hyperbole, and then the surface of that hyperbole would be the plane of that hyperspherical model.
So in case of R4 or S3, so here, if I define a plane, then let's say x1 squared plus x2 squared plus x3 squared is equal to r squared, where x4 is 0. Is it a plane?
Yes, I think so. Yeah.
Okay, so here, if it is, okay, so if it is, let's say, r to the n or s to the n minus 1, then the planes are really nothing more than any points which are at the same distance when we collapse some of the dimensions. Is it the case?
I'm sorry, but could you please explain it again? Like
so here, I'm trying to figure out the exact definition of plane. Okay, so I'm still not very sure about what is the definition of the plane. So if it is r to the 4, we have x1 squared plus x2 squared plus x3 squared plus x4 squared, right? Is r squared. Now, if that is a sphere, that a hypersphere that we are dealing with, then I suspect that x1 squared plus x2 squared plus x3 squared and x4 is 0 is equal to r squared. That one I suspect it might be defined as a plane. But what I'm not sure is exactly what is the definition of a plane. Is it, no, we cannot even make it as a subspace. So it seems like any 2-dimensional subspace within the spherical model.
I know what you mean. I think we can make an analogy between the Euclidean space and the spherical space. So if we consider in Euclidean space, let's say we have this kind of plane, and if we have for example, R4 stuff, and then each x1, x2, this kind of pair would form a plane, right?
Right.
And then the point set of the Euclidean space is still this R4. And for a hyperspherical model, then the point set of a hypersphere would be, for example, x1 square plus until x4 square equals some r square. R is the radius. And then for a plane, then it is the same as in the spherical model. So it's like if we have any pair of x1, x2, and x3, I think. And then such that x1 square plus x2 square plus x3 square equals let's say R0 square, and then this would be a plane.
So in case of regular Euclidean geometry, I have a very clear definition for the plane, which is that if it is, let's say, 4 dimension, then ax1 plus bx2 plus cx3 plus dx4 is equal to some number, let's say k. That whatever set of xi's that satisfy the relationship, that is the definition of a plane, right? Very straightforward to define it that way. Or is it actually, it is a hyperplane. It is a hyperplane.
Yeah, I think that should be a hyperplane instead of just a plane. So if we say it's a plane, then it's definitely a two-dimensional stuff in the Euclidean space, right?
Oh, so if you want to have a two-dimensional plane, then we have to have, if it is n dimension, then we have to have
then it's like x3 equals x4 equals x5 equals, for example, actually we only have x4 for this one.
No. So that is not general enough, because we cannot just assume that it is along a particular.
Yeah, let's just say it's some x3
right,
equals some fixed value, and x4 equals some other fixed value.
No. So even that is not general enough. The definition is that we have two equations where a1x1 plus a2x2 plus a3x3 plus a4x4 is equal to a5. And then b1x2 plus b2x2 plus b3x3 plus b4x4 is equal to b5. So any points that satisfy both of them, those are the planes for any kinds of ABs or ABs.
Oh, yes.
General definition. So can we somehow have something similar for the spherical model as well? Because I don't like zeroing out only a particular coordinates, and that one is not really general enough for definition in the way that I see it. So can we have something similar? Do we have something like what you showed earlier?
So for this question, I don't think I can do all the derivations right now, and I don't have a concrete conclusion yet, but I think we can make analogy to the Euclidean space and do things similarly. Like for Euclidean space, we can imagine that any plane, after we like change the coordinates, they can have some form like this, right? So, and then for a sphere, I think we can also think if we change the.
That's a good way to think of it.
Yeah.
Okay.
If we change the coordinates, and then let's use xi hat to indicate the coordinates under the new coordinate systems, and then as long as it satisfies this constraint, then this is a sphere.
I see. Oh, that's a good way to explain. Yeah, I think I got the basic intuition there. Okay, thank you.
Yeah. Okay. And so for congruent means that if we put them together, they can, it's like, for example, if we have this right angle and we have this right angle, and then if we mutate this one, and for example, we rotate it, and then we make this point and this point the same point, and then we rotate this right angle, and then these two are exactly the same, they're identical. And then for this one, it's also the same. So we have this right angle, we have this right angle, and then if we make this points to be this point, and then we rotate this one, for example, for 90 degrees, and then these two right angles can, these two right angles are exactly the same, and then that means congruent. Yeah. So hopefully I explained this clear. And then the difference of this postulate set between the spherical model and the Euclidean model is that for this parallel postulate, so we can find that it is not satisfied in the spherical model. So in spherical model, actually given a line and a point that not on this line, then we can never find a parallel line. So this is because, for example, we are given this red line, and then we are given this red point. And then we can, as long as this point is not on this line, then we can never find a line through this given point that is parallel to this line. So for example, we can find this line or the other lines, but all of these lines would have intersections with this big circle, because any of these two big circles, two great circles on a sphere, they would have intersections, therefore they cannot be parallel. So for the spherical model, given a line and a point, and then no parallel line can be founded.
So here the definition of parallel means that no intersection.
Yes.
Okay.
And then that's for the spherical model. And just one more comment, we also mentioned this problem before. So for spherical model, it's actually just 3-dimensional stuff. And we can simply generalize this spherical model by putting it into a higher dimensions and get a hyperspherical model. So the generalization process can be analog to the Euclidean space, where we generate from 2-dimensional stuff to a higher dimensional stuff. And for the spherical model, we can do it in the same way, and then we can get a hyperspherical model. And now let's take a look at another elliptic geometry model called the stereographic model. So first, we should note that for this stereographic model, the points and line and plane are defined same as in the hyperspherical model. And also for this model, the corresponding space is also a sphere, a spherical space. And then essentially, we can say that this stereographic model represents the same space as the hyperspherical model by means of the stereographic projection. So first, let's take a look at what is this stereographic projection. So we can see this illustration figure, this figure. And here, to give a more formal definition, the stereographic projection is a particular mapping that can project between a hypersphere, for example, this one, and a hyperplane. For example, this one, this large circle is a hyperplane. And by this kind of stereographic projection, we can project any node on this sphere to this plane. And then the question would be, how can we do this kind of projection? So first of all, we have to find a project point. We just call it project point. So first, we find this kind of point. It should be a point on the hypersphere, and then this point would correspond to the infinity point of the of this Euclidean hyperplane. And then, so every infinity point in the Euclidean space would be projected to this project point on this hypersphere space. And then for any node on this hypersphere, and then we connect the project point with this node, and then it will intersect with the hyperplane in this Euclidean space, and then this intersection point would be the corresponding projected nodes on the Euclidean space. So that's how we generate this sphere by using this kind of mapping. So we should note that this kind of, so given the spherical space, this kind of projection is a bijective one, which means it is a one-to-one mapping, except for the project point. We can note that if we consider an n-dimensional space and an n+1 dimensional space, and then the n+1 dimensional vector u and lambda u, well, this lambda is a scalar. They represent the same point on the n-dimensional space. So for example, if we have another spherical space, like for example this one, and these two spherical space have the same projection points, and then for this Euclidean space, we can see that this node and this node, they corresponds to the same points on the like hyperplane space, which is on this n-dimensional space. So that's the basics of the stereographic projection. And then as we mentioned before, the point, the line and the plane is defined in the same way as in the hyperspherical model. And then let's consider how to define a distance on this stereographic model. So the distance is defined differently than the hyperspherical model because we can see that this stereographic projection is the bijective projection. So to define the distance between the 2 points on the sphere, what we can do is we project them on the hyperplane with this stereographic projection. And then we define the Cordell metric for a pair of points on the n-dimensional plane. And if both points are not infinity, then we go with this one. And if so this delta value is the Cordell metric. And if one of the points is infinity node, then we just consider this one. So for this formula, U and V are the two projected nodes on the hyperplane. So for example, if we want to measure the distance between this point and for example, this point, then what we do is first we use the stereographic projection to project this node to here and project this node to here. And this will be U and this will be V. And then use this n-dimensional UV, we measure this Cordell metric, and then we take the 2 times arcsine value of half of the Cordell metric value, and then we can obtain their distance on the spherical space. So that's how we define the distance.
Exactly what are they trying to measure? I don't know what these formulas mean.
Oh, it's just measure the distance between 2 nodes.
Why do we use this particular formula? Like, why do you use arcsine? Why do you use this square root of 1 plus U epsilon square, 1 plus V epsilon square? Why are we? What's the meaning of these equations?
According to my understanding, I think this Cordell metric is already trying to measure the kind of the distance between U and V, and this arcsine stuff is trying to project it back to the hypersphere. So it's like, since I think this one can be regarded as some like length of the vector U, and this part can be regarded as some length of the vector V. And then for the numerator part, it measures their distance. And for this one, since we just have a infinity value, so we do not include that infinity in the formula. And then, so if we regard this V as infinity, and then we have this is infinity and this is infinity, I think that's the reason why we get rid of this infinity in the denominator and infinity in the numerator, and we have this formula. So this Cordell metric is already some kind of distance measure. And then for this arcsine, we just want to go back to this spherical space. So that's my understanding. And
that the distance is just a given, but I believe there are some very nice geometric interpretation behind it. Right?
Yeah.
So for example, you have this 2 points, UV. So essentially there are two ways to understand this UV. they refer to the 2 points in that sphere, right?
This U and this V refer to the projected value on the n-dimensional space.
Right.
And for this one,
they are corresponding to some points back in sphere.
Let's just big U and big V.
Okay, yeah.
And
so then this big U and big V, right? So they are in the 3D Euclidean space. Let's consider just a sphere to make it simple. So then we will have coordinates for big U and big V in this 3D Euclidean space, right? And then we through this stereographic projection, and usually we're going to have 2 copies to handle that 2 projection. Like this is from North Pole, but we also can do that from South Pole. So
I think usually we just consider the North Pole and we just ignore.
Okay, so for something I raise like from to both North Pole and South Pole to make sure that we can handle those South Pole and the North Pole, those 2 points as well. But anyway, my point is not like that. It just come to my mind. So then for U and V, it's like 3D coordinates, right? And for the small U and V, essentially we can imagine if we assume like the South Pole is kind of the 3rd dimension 0, right? So then we can also represent the small U and the small V in this 3D Euclidean space, right? So here, when we define the distance between U and V, I think somehow we are interested in the distance matrix of that big U and big V in the spherical space, right?
Yes, yes.
Somehow we want to define that according to this U and V coordinates in that 2D Euclidean space. So I think it's like geometric interpretation.
This should be big U and big V actually. So the distance between the big U and big V should be defined as this arc sine of quartile metric of small u and small v. So according to my understanding, I think for this quartile metric, it provides a distance measurement for small u and small v on the Euclidean space. And then for this distance big U and big V, it tries to go back from the distance between this U and this V to the distance between this U and this V.
Yeah, for example, what's the geometric interpretation? Because if we look at the big U and big V in that sphere, we still can utilize that geodesic distance from U to V as the distance, right? But it's just difficult to compute. Then is this like Cauda matrix provided the way to compute that distance? Because essentially we're still interested in a very natural distance defined on the spherical, and maybe that's difficult to compute. So that's why we need to first map it into Euclidean space, and then based on that we can that.
I just have one intuition. So let's take a look at one simple example. So we consider this is, so instead of consider this U and this V, let's just consider this as big U and this South Pole as big V.
Yeah, and so then it should be pi, right?
Yeah, and then the distance should be pi. So that's the, so if we consider the center of this ball, and this is their value, this is pi. So I feel this distance should actually measure the degree between, so this is the center of the sphere, that should measure the degree of this
right.
angle.
Now I think that delta UV somehow measure the distance of that arc.
Yes, half arc, I think, because we still have 2. So I don't think it's this arcs, because if it's this arc, then since we have this 2 before the arc sine function, then we are not going to measure the we're not going to measure the angle of the degree of this angle. So I think then this distance should measure the arc of one point to the midpoint of this arc. Is that clear?
Yeah, maybe, but I'm not sure. But somehow now I can understand if we look at delta UV, 1 plus mu norm square actually is the line starting from that center to that U. So we have the center for that sphere. If we connect that center to the U in the Euclidean space, then that should be 1 plus U square root.
So you mean this line?
Right. So that should be 1 plus mu norm square and take a square root. Right? That's the geometric meaning of that. And similarly, we can have that one. Yeah. And then this U minus V is just if we connect U and V together, right? So then I think there's like 1/2 AB sine theta equals to the area of that thing. Let me see.
So it's like this one times,
right?
Oh, and it divided by 2, so we can actually just consider it this way. Then it becomes the length of this line divided by the multiplication of the length of this arc and this arc.
Do you still remember given arbitrary triangle, right? So if we have A and B corresponding to the length of those two. Okay, let's say we have a triangle and we have A and B, and the angle between them is theta. So then the area of that triangle equals to 1/2 AB times sine theta, right? Okay, I try to make a connection. And that area at the same time in this case, okay, I don't know, but I just try to find the geometric interpretation. It has to have something.
Let me see. I cannot remember what is the formula for the sine value of a degree given all the lengths of the edges, but I feel this delta is trying to measure the sine value of this angle. And if we do arc sine, then we can get the degree of this angle.
Right.
And then somehow the angle, this angle is 2 times of this angle. I think I may need some detailed formulas to finish the proof, but I feel intuitively the logic is like this. Yeah, so essentially the distance is trying to measure this angle, and this angle is hard to compute, so we just do some kind of projection to make it easier to compute. And then since we have this angle is 2 times of this angle, then we only have to measure this angle, and then this angle can be measured with this kind of formula. So I think intuitively it should be something like this.
Right.
Yeah. And that's for the distance measurement. And then for the postulates, since we have that the stereographic model corresponds to the same space as the hypersphere space, as the hyperspherical model, then the postulates conclusions are the same, which means we have the first 4 postulates, but for the last one, it is not true, and we can never find a parallel line through a given point to another line. that's for the elliptic geometry, and then let's move to the hyperbolic geometry models. So the first model is this Poincare disk model. So this Poincare disk model is a two-dimensional hyperbolic geometry in which the points of a geometry are all inside a unit disk. So in this Poincare disk model, the point is defined the same way as in the Euclidean space, but also we have a constraint that it should be inside this disk. And we should note that for this disk, it's an open one, so a node on the boundary is not regarded as a point in the Poincare disk model. And then for lines, lines are actually defined as all the arcs of the Euclidean circles contained within the disk and are orthogonal to the boundary of the disk, and plus the diameters of the disk. So diameter is easy to understand. It's just something like this. So we have a center and every line passes through this center, and inside this disk is regarded as a diameter, and then that is one line in the Poincare disk model. And another type of line is the part of the circles. So we can see first this circle should be this circle is actually, we can say it's an arc that should contained within the disk and excludes the boundary nodes. Then we require this circle to be orthogonal to the boundary of the disk, which means that to measure this orthogonal stuff, we just, for example, for this node, this is the intersection, then we just have a tangent line of the disk, and then we have a tangent line of this Euclidean circle. And if their tangent lines are orthogonal to each other, then this circle is considered as orthogonal to the boundary of the disk. And then this part of the arc can be considered as one edge. We don't have to define the plan for this Poincare disk model because it is already in a two-dimensional space. So we can regard this whole disk as a plan. And then to define the distance of the Poincare disk model, we should use this K-Lakeland matrix. So in this figure example, assume that the boundary nodes are Q and P, and then we have B and A on a line. And then we want to measure the distance between A and B, then it is considered as a long function of AQ times BP divided by BQ times AP. So that's the distance measurement for the Poincare disk model. And then let's take a look at all the postulates in the Euclidean space and see if they can still be satisfied in this Poincare disk model. So for the first four postulates, again, we can say that they are still satisfied. So for any 2 points, and then we can only find one line. And also through any 3 points, okay, and through any 3 points, not on the same line, there's exactly one plan, because given any 3 points, we can just find this this unit disk. And then a line contains at least 2 points, and also all right angles are congruent. And the difference is still on the last one. So for the parallel postulates, it is again not satisfied for this hyperbolic geometries Poincare model. So in this model, if 2 lines are not, the definition of the parallel is still defined as if 2 nodes are not intersect, if 2 lines are not intersect, and then they're regarded as parallel. So in this case, for example, we are given this P node, and then we are given this line L. Then we can actually find infinity number of parallel line that is parallel to this L. So for example, all of this L1, L2, L3, L4, L5, they are parallel to this L. And we can, of course, have more lines as long as it satisfies a condition of a line and it passes through this P. So we can find many, many, many circles that are parallel to this L. So for the Poincare disk model, the parallel postulate in Euclidean space is not satisfied. And then let's move to the last example. So this is called the hyperboloid model. Some literatures also call it as a Lorentz model. So
sorry, can I ask a question about the parallel part?
Yes.
So actually that made me think the previous model, right? And the spherical model, right? When you say there's no parallel line, right? You can find.
Yes.
So a line here is defined as like it has to pass the because thinking about this ball, right? The spherical ball, right? And that a line has to pass the how to describe that? So because I'm thinking like a line could be like a it has to be like centered at the middle, is that right?
Yes.
That circle. So you can't really have a smaller circle somehow parallel to the bigger circle, right?
Yes.
Okay.
And then for this one, since we don't require this the center of the lines, so we don't have to require the center of these kind of circles.
Here the line is like as long as it's like orthogonal to the boundary, right?
Yes.
That's fine. Okay.
Yeah.
Okay, now I got it.
Okay, and now let's continue the hyperboloid model. So for this, so as I just mentioned, it is also known as the Lorentz model. So for this model, the points should be on the upper sheets of a two-sheet hyperboloid. So for the hyperboloid, so this is an example of a hyperboloid. So we can imagine that we have a hyperbola. For example, this can be a hyperbola. And then we have a like principal axis like this. And then we rotate this hyperbola for 360 degrees with this axis. And then we can get this two-sheet hyperboloid. So that's the definition of the hyperboloid. And then for the hyperboloid model, all points should be on the upper sheet, which is this part in the orange box. So this part is the set of points for the hyperboloid model. Then to define the line for this hyperboloid model, we should leverage the Poincare disk model we introduced before. So what we do is first we find a Poincare model, we find a unit disk. So how we're gonna find it is we give two tangent line of this hyperboloid, and then they would intersect at some point. And since this hyperboloid is symmetric, so this intersection point is definitely on the on this axis, and then we can find this point, and then we just put a unit disk, we put a Poincare model under under this hyperboloid sheet, and then its center should be the intersection point of these two tangent line and the axis. So that's how we build this kind of figure. And then to define a line, we can, for example, we have 2 points. We have these 2 blue points, and then we just project it in the, we just project it on the on this Poincare disk model, and then we can find a line on this Poincare model, and then we just project this line back to the hyperboloid sheet, and then we can get this brown line. This brown line is one line on the hyperboloid model. So that's how we get a line, and then that's for the line and the points. And then to leverage this hyperbolic model, it is very important to define what is the distance on or what is the distance measurement on this hyperbolic model. So to define the distance, first we have to define the Minkowski quadratic form, which is so given the n+1 dimensional vector x0, x1 until xn, it is equivalent to x0 square minus the summation of all the square of other elements. And then with this Minkowski quadratic form, we can have the Minkowski bilinear form, which is also known as the Minkowski inner product, which is the quadratic form of u plus v minus quadratic form of u minus quadratic form of v divided by 2. So to put it more clear, this is actually the same as this formula. So given a 2n+1 dimensional vector x0, x1 until xn, and then y0, y1 until yn, then the Minkowski inner product is defined as x0 times y0 minus x0 y1 until minus xn yn. That's the Minkowski inner product. And then for the hyperbolic distance, it is defined as the arc cos h value of this Minkowski inner product. And that's for the distance measurements. And then finally, in terms of the postulates, we can get very similar conclusions as in the Poincare disk model. So the first 4 postulates can be satisfied, but in terms of the last one, it's since we can always project between the hyperbolic model and the Poincare disk model, then we know that it should be so it should be, we should have similar conclusions. And for the line and the point that is not on that line, then we can guarantee at least 2 parallel lines. So the last parallel postulates cannot be satisfied for the hyperbolic model as well. And then that's all the examples for the hyperbolic geometry. So now let's move to the last key question we're going to discuss in this introduction part, which is the product space. So the motivation to have this product space is that the real world data might be very complicated, and they might not be structured uniformly on one certain manifold. So we may have varying structures, and then we may need multiple different manifolds to embed the data. So here a manifold means a topological space that can locally resembles Euclidean space near each point. So that's the motivation why we need to consider this product space to define this product space. Then we first have to introduce this Cartesian product, which is given in this example. So for example, if we have a set A include X, Y, Z, and we have a set B include 1, 2, 3, then the Cartesian product of set A and set B is a set of this kind of elements, and each element is a concatenation of one element from A and one element from B. So that's the Cartesian product. And then we use this Cartesian product to generate a more complicated space with just a simple manifolds. So for example, if we have a circle, and it should be a solid circle, and then we have a line, and then the Cartesian product of this solid circle and this line would be this cylinder. Another example can be, for example, we have this red solid circle, which has this kind of constraint, like the true norm of the vector y should be less than or equivalent to this radius r2. And then we also have a circle. This is not a solid one, so here, instead of having less than or equivalent to, we require it to be equivalent to the radius r1. And then if we have these two kind of different manifold, then we would get a donut as their product space. So so for the real world data, as it is very complicated, so we have to have this kind of product space to kind of combine, to integrate different simple manifolds and to form more complicated manifolds. So that's for the product space. And now we've already introduced some preliminaries of the non-Euclidean geometries, and then we can start to take a look at some papers to see how these non-Euclidean geometries can be combined with the graph neural networks. So now let's take a look at the first paper we're going to discuss today. The paper is called Hyperbolic Graph Convolutional Neural Networks, and is published in NeurIPS 2019. So the motivation of this paper is that, so for most of the existing graph neural networks, it tried to embed nodes or links or graphs into a Euclidean vector space. And also, most of the standard classification toolkit is available only for the Euclidean embedding. But however, sometimes it is not enough to only leverage the Euclidean space. So when given the inputs of as all the nodes in the graph and their features and the structures, and then for the learning stage, this paper discussed that we instead of simply use Euclidean embeddings, sometimes some non-Euclidean embeddings are having higher qualities. And then the output should be the same. So it is still fitting this input node features and structures, and then learn embeddings, and then output the node labels or edge labels, like they focus on the node classification and edge prediction task. So it still fills in this general workflow, but they just change the part of this embedding learning. And then, we should note that the graphs is sometimes it's very complicated, and it may have different properties. Like some graphs are just have many large circles, and some graphs are just grid-like graphs, and some graphs is more hierarchical, and it's a tree-like graphs. So intuitively, we can find that for the graphs with many cycles like this one, it is very similar to this kind of spheres. So it is with a positive curvature, and it is best with the spherical space embedding. And for these grid-like graphs, then it's very similar to the Euclidean space, and it's going to be best with the Euclidean space embedding, and that have a zero curvature. And for the hierarchical tree-like graphs like this one, it is best with the hyperbolic space that have a negative curvature. So now let's, in this paper, they focus on the hierarchical tree-like graphs, and now let's take a look at this kind of graphs. So first, this kind of graphs are usually very sparse, and they have a very small number of cycles, and then we know that this kind of graph usually would have exponential growth in number of children. And then if we define the volume of graph as the number of nodes within some distance to a center node, then we can see that this kind of volume would grows exponentially with respect to the distance from the regular trees. However, if we consider it is in a Euclidean space, then the volume of balls is going to grow polynomially instead of exponentially with respect to the radius. And that would lead to a high distortion of the tree embeddings, while the hyperbolic space, the volumes would grow exponentially. And that's the reason why we want to consider the hyperbolic space embedding. And then the main task setup of this paper is they try to conduct link prediction task and node classification task on these kind of hierarchical tree-like graphs. And then we can move to the method. So here is a method overview. So to begin with we have to know two very important mapping operations. One is called the exponential mapping, with which we can map from a tangent space, which is a Euclidean space, to a hyperbolic space. And the other is logarithm mapping, which is the inverse operation of the exponential mapping that we can map from a hyperbolic space to a tangent space. So I will give more details about this kind of mapping and the tangent space and hyperbolic space in the later stage. But for now, we just need to remember that this two kind of mapping is trying to map between the hyperbolic space and the tangent Euclidean space. And we would use a lot of this kind of operations in the following. Also in terms of the hyperbolic space, we also need to know that the curvature will be very important. So curvature measures like how unflat it is a space. So we can see that if we have a hyperbolic space like this, and we have a hyperbolic space like this, and of course, this one is more curved ones. And then for this one, its curvature is more close to 0 compared to this one. And this one is very negative. And then these kind of curves will give us a very good intuition about how this kind of curvature would influence the distance between two nodes in the hyperbolic space. So for example, if we have X and Y, these two nodes, and then we want to measure their distance based on this hyperbolic model, and then we consider its curvature. For here, the curvature is measured by -1 divided by k. So actually, this square root of this k can be considered as the radius of this kind of circle in the hyperbolic space. So we can see that when the curvature grows, and then the distance of x, y would drop. So it's like, for example, if we have two nodes, x and y, if they if we project onto a Poincare model, and then these two nodes are on the same position as the in the Poincare model, then with the smaller curvature, then their distance is going to be larger, and then with a I think it's going to be better if we take a look at this one. So if we imagine that this space is more flat, then the distance of this xy is going to be smaller. And then if this space is is more curved, then we can see that for this one, the distance between x and y, they might be larger than their distance in a flat space. So that's the reason why when the curvature grows, the distance will drop. So it's like when curvature grows, we will have a distance from this one to this one, and then the distance will drops. So for this overview part, we just want to know what is the exponential mapping, what is the logarithm mapping, and what are these two mappings doing. And then we should also know that the hyperbolic space with different curvatures would have different properties. So it will be very important to have a different trainable curvatures at different layers of the graph neural networks. And then let's take a look at the details of this hyperbolic graph convolution network. So first of all, we have to know that the input features, so this input transformation is actually the very beginning step, is the initial step of this network. So we want to map the input features to the hyperbolic space using the exponential mapping. So as we mentioned before, exponential mapping can help us to map from the tangent space to a hyperbolic space. So so this kind of mapping is like this. So we have a hyperbolic space, which is the upper part, and then we would also have a flat Euclidean tangent space, which is this one. And then we are mapping from here to here. So that's the initial step. So we are given the features in the Euclidean space, and then we first map it into a hyperbolic space. And then that's for the initial step, like we are doing input transformation, as I just mentioned before. So for here, this x0e is the initial embedding in the Euclidean space. And then we want to use this exponential mapping to map it to x0h, which is the initial feature on the hyperbolic space. And here are the formulas to do this kind of exponential mapping. And this step is the initial step and is only for the raw input. And for the later part, all the inputs of each HGCN layer would be in the hyperbolic space, not in the Euclidean space. So we don't have to take this kind of steps. And then for each of the HGCN layer, the input is on the hyperbolic space and the output is also on the hyperbolic space. And then we want to conduct the graph convolutional operations on this kind of hyperbolic space. And then the main steps include two parts. One is the GN aggregation. The other would be the update, in which we mainly deal with the non-Euclidean transformations. So for the aggregation part, essentially we can write it this way. So we try to have some W's to aggregate the node the node representations from each node's neighborhood. And then we can imagine we're doing things this way. So we try to first use a logarithm mapping to map from this Euclidean space to this from this hyperbolic space to this Euclidean space. And then we can use the Euclidean operations, the summation, the multiplication, this kind of operations to handle the aggregation. And after we obtain the aggregated representations for each node, then we use the exponential mapping to map it back to get the output of this layer. So instead of simply use the normalized adjacent matrix to aggregate the neighborhood for each node, in this HGCN paper, they try to use a attention mechanism to aggregate the features. So essentially, the attention is computed by concatenate the mapped representation for node I and node J, and then we take a MLP, and then we take a softmax outside. So for this log one, you can just imagine it is actually XIE and XJE. So E means in the Euclidean tangent space, H means in the hyperbolic space. So we can compute the attention based on this network, and it is trainable. And then we use the attention-based aggregation to aggregate the representations. So for this one, we can think it as XJE, and then we use the Wij as the attention to do the aggregation, and then for each node, and then we can obtain its attention-based aggregation this way, and then this part is on the Euclidean space, and then we use exponential mapping to map back to the hyperbolic space, and then finally we can get the output of this layer, which is in the output of the attention-based aggregation, which is on the hyperbolic space. And then the next step would be the update, which is trying to apply the nonlinear activation to the tangent space projection. So essentially, now we have the output of this one, and then again, we use a logarithm mapping to map it to the Euclidean space, and then we can use the like item-wise nonlinear activation, such as ReLU in their implementation, and to do the to add the nonlinear part to this network. And then after we take the nonlinear activation over this representation on the Euclidean space, then again we use exponential mapping to map it back to the hyperbolic space. So we should note that all of these curvatures KL, so for different hyperbolic space, we have different curvatures, and then all of these curvatures are trainable. So for different layers, they may have different curvatures, and then that's the full output of one HGCN layer. And
I just want to clarify this. So actually, all these operations are still done in the Euclidean space, right? So they are just mapped back. It seems that they map back, right? For the GCN part, and then so all of those GCN computations are still done in the Euclidean space.
Yes. So it's like they have, this is input. I use this to indicate a Euclidean space. And then for the first layer, it is probably like this. This is one hyperbolic space layer. And then the next layer would be like this, for example. And then maybe next one, this one. And then the output is feeding to a decoder. And then we will get the output in Euclidean space again. And then for each of these parts, it's like we first have this one, and then we map it to the Euclidean space to do the GCN operations, and then we map it back to this hyperbolic space. So it's like this.
Okay, so which operation they're doing in the hyperbolic space?
I think the main difference is in this curvature part. So the curvature is in the hyperbolic space. So essentially through this kind of different mappings.
The curvature is learnable, right?
Yes.
The curvature is learnable parameter, and then so that's the only thing in the hyperbolic space they are actually learning.
Yes.
Okay.
And for other operations, they are in the Euclidean space.
Okay, so everything else what they learn is in the Euclidean space. Okay.
Yes. And then the next would be the experiments. So essentially they use two tasks, link prediction and node classification, to evaluate their model, and then they compiled with the Poincare embedding the some hyperbolic neural networks with no graph information. So this is some work in, I think it's in computer vision domain. So they also adopt this model for the graph setting, and the drawback of this baseline is it does not include any graph information. And then it also consider compare with the graph neural network variants in the Euclidean space, such as GCN, JT, GraphSage, and SGC. And here's their results. So first of all, we have this delta, which is the Gromov's delta hyperbolicity. So it can measure how tree-like is a graph. So if we have a low hyperbolicity, then we know that it is more tree-like and is better with the hyperbolic space. And we can see that for those with very small hyperbolicity, and then on average, we can have a 9% performance gain in the link prediction task. And we can have 7% in the node classification task. However, when we come to the PubMed and Quora, these two are very frequently used data sets for the node classification and link prediction task, but they are more like a non-hierarchical data sets. So we can see that they have a very low hyperbolicity. And then the performance gain is very marginal. And even for this Quora with a very large hyperbolicity, which means it, which has a very low hyperbolicity because we have a very large delta. And then for this data set, the performance is even less comparable to this kind of Euclidean space graph neural networks. So we can see that their experiment results demonstrate that in the hyperbolic data sets, their method is very effective, but in a Euclidean space data set, then their model is less powerful, but still very competitive. And this also demonstrates that for different for graphs with different properties, we should have different types of graph neural networks. We should use different embedding space to do the node embeddings. And that's all for this hyperbolic graph convolutional neural networks paper. And then let's move to the second paper, which is this constant curvature graph convolutional networks. And this is published in ISML 2020. So first, an overview. So the main motivation is actually the same as in the hyperbolic graph convolutional neural networks paper. So essentially, we want to use different embedding geometries to embed the nodes in different types of graphs. And their main contribution is that they try to provide a unified formalism to embed the graphs into not only hyperbolic space, but also the spherical space and their product space. So which means for this paper, they can handle more complicated graphs. So they can handle the hyperbolic space, they can handle spherical space, they can handle product space, and they can also handle Euclidean space. And their key idea is to leverage the K stereographic model. So, and then in this case, stereographic model is actually a geometric model that can capture all three geometries of constant curvature at once. So, so if we still remember that previously in the elliptic geometries, we introduced the stereographic model, and then that's not the same as this kappa. This case actually kappa. So that's not exactly the same as this kappa stereographic model. So this kappa stereographic model is a more generalized version and can handle all the constant curvatures, no matter it is 0 or positive or negative. And then to begin with, let's first take a look at this kappa stereographic model. So first, we should note that the hyperbolic space is not a vector space. So to define the kappa stereographic model that can capture all these three types of geometries of hyperbolic, Euclidean, and spherical at once, we should consider this zero space. Which is not exactly the same as vector space, but it's very similar. And then it also have to define its own summation, multiplication, and some normalization, this kind of operations. So we can make analogies between these zero spaces and the vector spaces. So for these zero spaces, it is also called as a zero vector space. So we can regard it as a more generalized version of vector spaces. So I'm not going to go very deep about this zero space. So if you are very interested, you can refer to this blog over here. I just provide a link. And this blog introduce this kind of zero space, I think it's very clearly. And then with this kind of zero space, let's just regard it as a generalized version of vector space. And then we can define this Kappa stereographic model. And then we can, actually this Kappa stereographic model is kind of an instantiation for the zero space. So and then we can then for this case stereographic model, we should redefine the summation, the multiplication operations. And then first of all, we should know that for this Kappa stereographic model, any nodes inside this model, any point inside this model should satisfy this kind of constraint. So essentially it is still a dimensional vector, but we should require that the negative kappa times the 2 norm square should be less than 1. Where this kappa is the curvature of the space and d is the dimensionality of this x. And we can note that if we have this kappa larger than or equivalent to 0, which means it's a spherical model or it's a Euclidean model, then this set is actually same as our D space. And then if k is less than 0, which indicates it's in the hyperbolic space, then we can regard it as an open ball of the radius of square root of -1 divided by k. And then we redefine the summation operation, and we redefine the multiplication operation, and then we also redefine the unit speed geodesic operation. So this unit speed geodesic is saying that if we want to move from the x point to the y point, so y is the destination, and we are using a unit speed, and then t is the time, then if we start from x and then use a unit speed, and then after t time, and then what's the location of us, then we can see that if in the Euclidean space, we have this one, and then if it's in this Kappa stereographic space, then we should have this one. So we just redefine these 3 sort of operations, and we also redefine other operations in the zero space and in these case stereographic spaces, but we are not going to use them in these papers, so I just do not introduce the other operations. And also, with this Kappa stereographic model, we can start to introduce this constant curvature graph convolutional network model. But first, we have to clarify some important formulas. First is, again, this exponential mapping. Similarly as in the hyperbolic graph convolutional network paper. So this exponential mapping is trying to map from the Euclidean space to the K stereographic space. And then we also have the logarithm mapping, which is the inverse operation of the exponential mapping. So essentially it is trying to map back from the K stereographic model to the Euclidean model. And here are the formulas of them. And then we should also know the nonlinear activation in this stereographic model. So essentially it is defined as like we first conduct a logarithm mapping to map from K stereographic model space to the Euclidean space, and then we just use Euclidean space level non-linear activation, and then we just map back to the Kappa stereographic space. And here are a clarification of all the notations. So we should notice that this V should be a point in the Euclidean space, and this green X should be Okay, and this green X should be the north pole, and then this blue Y should be the point in K-stereographic model. And for this line, then this green 0 is actually the same as this green X, so they are regarded as north pole. And this orange X is actually the same as in the V in this exponential mapping formula, and they're regarded as a point in the Euclidean space that we are going to map. And these are the main formulas we are going to use when defining the constant curvature graph convolutional network. And then for this constant curvature GCN, there are three main steps. One is the right product operation, which is the XW in the GCN. And we also have left product operation, which is AX in the GCN. And then we also have the nonlinear part. So combining all of this part, then we would have the constant curvature GCN. So let's first take a look at the first step, which is the right product operation XW. So similar to the hyperbolic GCN paper, essentially we can understand it as we map to the Euclidean space. Like here, this is mapped to the Euclidean space, and then we do this kind of XW. And then after we have the, we finish the right product operation in the Euclidean space, then we just map back to the hyperbolic space, to the kappa stereographic space. And then for the left-hand side product operation, which is this AX, what we do is actually still very similar to the operations in the Euclidean space. So it's like we do this kind of multiplication where this MK is the weighted midpoint in the zero space. So like this. And so for this formula, each lambda is defined with this formula. And then the alpha is the is the weight, which corresponds to an entry in this A matrix. So essentially, we just try to get the mean value of the representation of this node and all its neighborhood. So that's for the left product operation. And then finally, we have the constant curvature GCN, which is, so first we have this A hat matrix, which is equivalent to conduct this kind of symmetric normalization of the augmented adjacency matrix A. And then this is the left-hand side operation, which is defined in the second step. And this is the right-hand side product operation we define in the first step. And then this structure is in general very similar to the GCN structure, just the operations are defined differently. And then finally, we have this kappa stereographic version of the nonlinear activation. As we mentioned before, essentially it's just a project to Euclidean space and do pointwise nonlinearity and then map back to the kappa stereographic space. So for that's a full constant curvature GCN layer. And for here, this kappa is a hyperparameter instead of a learned one. So that's one difference compared to the hyperbolic GCN paper. And then also to improve this method, so that's the that's a basic architecture of one layer of constant curvature GCN, but we can also improve this method. So instead of consider a very simple space, we should also consider a more. We should also consider that. As we mentioned before, the data is not structured so uniformly, so we have to consider this product GCN. We will have to consider this product space, and then this paper just proposed to learn the embedding in a product manifold combining multiple copies of the model spaces. And that's their motivation to propose this product GCN. So essentially, it's like we have, for example, a hyperbolic space, we have a spherical space. This is of dimension 8, and then for this product GCN, what it does is it do the constant curvature graph neural network. Okay, so this is, let's just call it CC because constant curvature, and CC GCN with hyperbolic space of hidden dimension 8. And we have another CC GCN layer with the spherical space of dimension 8. And then this one have, then this one would have a learned representation, and this one would have another learned representation, and then we just concatenate them together as the final representation learned by this product GCN. So that's what this product GCN is doing, and that's how they consider the product space stuff. And then they test their model on the node classification task on some frequently used dataset like Scier, Cora, PubMed, and the LPOR dataset. So for this table, this E indicates Euclidean space, H indicates the hyperbolic space, S indicates the spherical space, and this number on the upper right corner indicates what is the hidden layer size. And then we can see that for different data set, like different space would have different performance. And for Scier, it prefers this hyperbolic space. And for Cora, it predicts this, it prefers this spherical space. And if we still remember the results from the hyperbolic GCN, we can see that this Cora has a Gromov hyperbolicity as 11, which is very low, and this is a very large number, and the hyperbolicity is very low, so it should prefer a spherical space. So that's this also matched our previous intuition. And for PubMed, it's also best with the hyperbolic space, and LPOR also hyperbolic space. So it turns out that again, it is very important to choose different embedding space for different data sets. And then let's compare the HGCN paper and the product GCN paper we introduced today. So for HGCN, it is only on the hyperbolic space, and it cannot handle the Euclidean space and spherical space well, but it have a learnable curvature. So in terms of the curvature, it's very flexible. And for the product GCN we introduced today, it is the benefit is that it is a more general framework, and it can handle hyperbolic space, Euclidean space, spherical space, and even the product space. But the drawback is that the curvatures are hyperparameters, which is not learnable, and this part is less flexible compared to the HGCN version. And also for this product GCN, we have to, even if it can handle hyperbolic, Euclidean, and spherical space and product space, we have to find this kind of space manually. So we have to predefine everything and then try to test like which space is the best. So that's also something probably can be improved. Okay, and then finally a quick summary. So for today's reading group, we mainly discussed 2 papers and some backgrounds of the non-Euclidean geometry. So in the gentle start, we discussed what is Euclidean geometry and what is non-Euclidean geometry, and we also give examples for elliptic geometry and hyperbolic geometry. And then finally, we introduce the product space that can handle a more complicated real-world data. And then we introduce hyperbolic graph convolutional neural networks, which only performs well on the hyperbolic space, but it have a very flexible curvature. And we also then we discuss the constant curvature graph convolutional network, which can handle different types of geometry embeddings, but it have a very it has a fixed curvature, which is less flexible and probably can be improved. And here are all my references. So if you are very interested in this topic, then probably you can take a look at this set of the references. And I'm more than happy to have offline discussions about all of these papers and about in general about this topic. So that's all of my presentation today. So do you have any questions?
Okay, thank you, Yewen. So
Okay.
I just did some like search online, and I think the distance between any 2 points in the sphere actually indeed is the angle of those 2 points. Yeah, so then from this geometric interpretation, I think probably we can follow. Let's see how we can prove that. I think it's almost there. Just yeah, maybe need some. Like,
okay.
Yeah, another question is like right now when we're talking about this projection, right? We just based on like just a North Pole, but then that will cause trouble in the area around North Pole, right? Because for that particular point, it will be mapped to many points.
Why is that?
The North Pole itself.
Yeah, except for the North Pole itself is not a one-to-one mapping, but other nodes are one-to-one mapping.
Right. The question is like, will that cause any issue?
I personally do not think so, because in the Euclidean space, when we say infinity, we do not say like which infinity. We just say every infinity is infinity. So for the infinity points, they do not like have like different infinity points. We just say we have one infinity point. So I think that should be fine.
But computation-wise, right? So we still need to represent that in, for example, 2D space. So suppose we want to map this 2D sphere into like a 2D Euclidean space. If we really want to represent that node, then it could be anything, right? Like computational-wise, if like think about how computer can internally represent the embedding for that particular point, then it could be anywhere where the norm is very large.
I see.
I mean, there's like gap, like theoretically probably is fine, but interpretation-wise, whether that will cause issue.
I think if implementation-wise, then we just like if the norm of this node is infinity, then we'll just go to this.
Yeah, but anyhow, so then infinity is just a relative number, right? So I mean,
I see. I see. For example, if we have two-dimensional and one-dimensional is one, the other point one-dimensional is 2, and then for both points the second dimension is infinity, then the distance between these 2 points is not 0, but in the elliptic geometry, then the distance of these 2 points is 0. So do you mean that?
Yeah, what I mean is like when we want to store this number in computer, then we cannot really store infinity. We do not have like a spatial symbol for it. It's just we still need to represent as a concrete, like 2 numbers. So then how to decide it, it's already go to infinity. That's kind of tricky. So that's why like in a more theoretical kind of analysis, right? So people try to use 2 projection points. So including both North Pole and the South Pole. So in this case, right, so the North Pole can have a unique representation when we do the projection from South Pole. And
I see.
So in this way, right, so even like in one projection, like, we do not have a kind of unique value, but from the other projection, we still have the unique value. In that way, then we can take care of the 2 spatial points.
I see. Yeah, I think that makes sense to me. Okay. Thank you very much for your comment. And
thank you.
yeah, if we don't have other questions or comment, then I just stop sharing my screen, and that's all for today's reading group. Thank you.
Okay, thank you. Bye.
Bye.
Thank you. Bye.